Hey there, Calc 2 folks, back here with another Mathematica demo that I want to put together for you. Where in this demonstration I want to show you how you can use Mathematica to develop a code for calculating these interval approximates of our convergent infinite series. As we go back into the notes, there were the case for approximating a non-alternating series, and there was a way of approximating a non-alternating series with an interval approximate, and then we had an interval approximation technique for approximating what we have for the case of an alternating series, right? I want to spend this demo showing you how you can put together some of those approximations. If we take note, to begin with here, we're going to want to first of all open up a notebook, right? Don't forget to give your notebook a title, because Mathematica will save it under a very random title if you don't give it a name, and you'll have a hard time finding it later on. So give it a good name to find it later, right? I'll go ahead and call this approximating series. Here on the input bar, I'm going to go ahead and hit Alt-4, and that's going to open up for me a title window here. And I might say here, let's call this interval approximates of non-alternating series. Let's go ahead and give that this title. I'm going to use the cursor key to curse down one, bring back the Mathematica window, and then I know this doesn't show up in the video, but if you hit Alt-8, that'll open up a gray cell where you can actually record. Well, it's known as a code cell, right? And this is kind of a way that I like to highlight my codes here, folks. So, and what we are going to be developing here, if I bring this into view, is we are going to consider this calculation here, right? If I bring that calculation up, all right, now it's not showing. Let's see here, maybe I will, let me pause this. All right, I have it right here. I brought this up. This is the theorem in a bit of a condensed form for what gives us the interval approximation of a convergent non-alternating series here. And again, if you go back to that theorem, remember it begins by assuming that what you have given for S is a non-alternating convergent infinite series where C is going to play the role of the lower index for K, and this series is going to continue its summation up through infinity, and A sub K, when we think about its value, it could be thought of as being able to be expressed as some explicit function of K, some explicit function of that index. And what we saw in the theorem was that an interval approximate of S, right, the value of this infinite series, if it's convergent, can be calculated to be between these two outer bounds. This value of S can be calculated to be bigger than this value S sub n plus this improper integral from n plus 1 to f of x dx, and that value of S can be calculated to be smaller than this upper bound, S sub n plus the improper integral from n to infinity for f of x dx. All right? Where this interval approximation for S does involve these two improper integrals, right? And we're going to use Mathematica to set up their calculations, as well as they also involve this value S sub n. This is where S sub n, we understand, is that the sum of the first n terms in the sequence or series. And what we were trying to do here is use S sub n as a means of approximating the value of S, right? So this S sub n is going to be part of our calculation. We're going to work that into our calculation here. All right. Now, where we do begin in our coding here is we do want to go ahead and declare our function f at k. All right. So in Mathematica, to declare a function, you are going to use a bit of function notation. Right. Here I see this function f of k being used, right? Where it certainly appears to look a lot like function notation. However, in Mathematica, to clearly define a function, right, using this notation, you do want to follow the independent variable with an underscore symbol. And that's what we have going on here, is we have f at k with an underscore following the k. Now let's go ahead and declare this to be an convergent infinite series. Now we know 1 over k squared is a convergent p series where p equals 2. So let's go ahead and go with that case, 1 over k squared here. And to begin with, that is our function f of k, right? We're going to need that to begin with, where then I might follow this with our infinite summation, right? Or our partial summation here is both going to start at a lower index of c. So when we consider forming this summation and developing its calculation, we are going to want to take note on what is our lower index in the calculation. That lower index will affect the value of our approximate. So we want to have it as a variable that's declared in this program. So where we might naturally start 1 over k squared will not be at 0, because 0 would certainly produce an undefined term for the first term. But let's go ahead and start it at the value of 1, right? That is going to be the location for my lower index of k, right? That is going to be the value from this lower index on k in these infinite summations or in this sequence of partial sums. Now, in this interval approximate, in the value s sub n and in the values of these improper integrals, involves the value of n. N being this term that we're summing up through in the this partial summation given by s sub n. So what we might also want to declare as a variable here to begin with is that value of n. And in this first case, we might just consider summing up through the first 10 terms. So let's go ahead and make n equal to 10 here, right? Now, those are some of my initial variables that I'm going to use, as well as my function. And what I'm now going to follow with is actually putting together the calculation for s sub n. I'm going to have to develop this summation calculation. As for the value of s sub n, right, s sub n is going to be a sum, right? What we are going to sum is function f of k, and f of k is going to be summed over values of k that start at 1 and continue up through the value of n, or really I should say starts at c, that lower index that we can set early on with our variable up here, and continues up through the value of n. Now, if I don't declare this and I go ahead and run that as just an equal, I believe we'll see that summation. Yep. Here's the sum of the first 10 terms of this convergent geometric or p series where p equals 2, right? The sum of the first n terms is going to be this ratio value. Now, if I want to give that an index, oh, careful there. If I want to understand it as a bit more of a decimal value, we could take the what we call numerical approximation of s sub n. Here I'm applying the operator n to s sub n, and what this is going to do is give me the numerical approximation of s sub n. It's going to give me the decimal, right? If I input that, we can see that my value of s sub n given in its exact rational form is followed up with this decimal approximation. Now, that decimal approximation does round out to 5 decimal places. It does use 6 digits of precision. We could note that that is what is set by default in Mathematica. However, if we wanted to change those number of decimals in precision, we could do that. We could consider using 9 decimals of precision here, or 9 digits of precision, right? And our approximation would be given back with those 9 values, right? Or we could use 90 if we wanted to, right? And we could get an approximation out to 90 digits in precision, right? And you can see here the calculator is really good, or the Mathematica is really good at expanding out to any decimal degree that we're interested in, right? But I'm going to go ahead and leave it alone for now. Let's just go ahead and leave it in the default here for just a few digits of precision, right? And let's next consider calculating these lower and upper bounds on our approximation for the value of r. Sub n, the remainder here. If you remember, this value here and this value here were the bounds on our remainder, using s sub n to approximate the value of s. This we understood was a lower bound on that remainder. This is what we understood as an upper bound. So let's set those up here in our calculation. Let's talk about having that upper bound, right, as well as that lower bound. And I'll go ahead and just use the variables upper and lower, or up bound and low bound, to stand for those quantities. And as we note, the upper bound, this bound here on the right hand side of our interval approximation, this case for this improper integral from n to infinity for f of x dx, right? That is going to come about from integrating. We're going to integrate function f of k, right, for values of k starting at the value of n and continuing up through the value of infinity. Now, I will tell you, this is an improper integral that we're calculating, and Mathematica doesn't like improper integrals. So you'll notice this is, if I hit enter here, it does give me the value 1/10 here, right? But it will at also times give us an error message. So we really want to be careful here. Properly, what we should be doing is putting in an upper bound of b and coming back and applying a limit to this calculation. If I consider the limit then for the integral of f of k from k starting at n up to b, I can then make b approach the value of infinity in this limit. Now notice, to make this arrow symbol here, that approach, I am using a minus sign followed by a greater than symbol without the space. And when I bring those together, you will see I produce that, that right arrow, right? Now if I hit enter here, it should give me back also that value of 1/10. It handles that limit without much difficulty. Now that is my upper bound. I'm going to go ahead and copy this over for my lower bound. In terms of my lower bound, it's going to look similar to this, except start at n plus 1. So my lower bound will be at n plus 1. And if I hit enter, right, we do see that that result gives me 1/11 in value, right? And what I want to do with these lower and upper bounds is I want to add them on to the value of s to form this interval approximation. As for the interval approximation, we might highlight that here. We might say, let's print the statement, the interval approximate of this series where a sub k equals f of k, right, is as follows, right? So let's go ahead and declare that out as this following statement. This is the interval approximation where our value of a sub k in that series is equal to this explicit function of k, 1 over k squared. What we are going to need is the value s sub n, and add that to our lower bound, right? And follow that with s sub n added to our upper bound, right? Now when I believe I hit enter, it will actually call out this interval approximation. It says the interval approximation of the series with a sub k equal to f of k, where I could, if I wanted to, actually come along here and say, well, let's highlight that specifically as the value that, comma, comma, and then I'll put in here f of k. Let's actually declare f of k in this argument so that we're clear as to, in the result, what was the series of interest. Now, I think if we hit enter, we will see that declared, yes, right? And actually, let me put in an equal here in a space, and that'll give us some nice spacing, right? The interval approximation where a sub k equal to f of k is equal to 1 over k squared is as follows. Now, it gives me this interval of approximation in a decimal or in a rational form. To obtain the approximation in a numerical form, I could wrap this set of values, or this group, right, with that numerical approximation operator. And now if I go back and I hit enter, I do get the numerical approximation also for this series. All right. In a sense, what this is telling us, right, is when we approximate the infinite series for 1 over k squared, starting at 1 and continuing up to infinity, it is somewhere between 1.64068 and 1.64977 in value, right? This value of s is somewhere between this value on the left, which is given by 1.64068, and this value on the right, which is given by 1.64977 in our interval approximation. All right? So, again, folks, this is our first program here that we wrote where this will actually develop an interval approximation for non-alternating series for the case of a convergent non-alternating series. And as long as we're dealing with a convergent series, we can approximate it this way if we can integrate that series. For instance, I could come back and consider, well, what about if we were to take k plus 3 raised to the third power, 1 over k plus 3 raised to the third power. And let's consider using an approximation that sums up through the first 100 terms. Right? Now, I will get some outrageous radicals here, or rationals, I should say. This is certainly an outrageous rational, and when I actually think about the series as this rational value on the lower bound and this rational value on the upper bound, I do get some outrageous rational values. But with those numerical approximations, here's the numerical approximation of s sub n. This very large, outrageous rational is equivalent to just this decimal. And the boundaries we get by adding that to this and adding that to this, right, gives me these definitive bounds here, right? And we can see these expressed using that numerical approximation, where we end up with these decimal values. Taking the quantity 1 over k plus 3 cubed and summing that starting at 1 up through infinity, right, has a value somewhere between 0.0400194 and 0.40 or 0.0400203, right? We develop this interval approximation of that value. S must be somewhere between these two decimal values for this particular infinite series, the series whose arguments look like this and begin at the value of 1. Right? And maybe we ought to point out here, let's say here maybe starting at c equal to, let's put in here the value of c also. And there we go. We get something like this. The interval approximation of this series starting at this value of c is as follows. All right. And if we wanted to turn off some of these values, right, if we wanted to only strictly stay with the numerical approximations here and avoid some of these crazy radicals, I could put semicolons at the end of the statements that are printing out some outrageous values, and hit enter now, we should get a nice clean result. Here is s sub n, right? We might note here print the sum of the first we'll say here, n terms of this series is as follows. All right? It is this following value here that we're going to get. And if I go ahead and hit enter, right, we have that cleared out. The sum of the first 100 terms is this. Right? The interval approximation of this series then, starting at c equal to 1, is then this here. Right? And we get, Mathematica does this calculation for us very conveniently, we might say, with this program. Right? So let me take a quick break. I'm going to come back here and I'm going to set up for you here the case for an alternating series, which is actually a little cleaner in its calculation. I'll be right back with that. All right, folks, I went ahead and started to set up this calculation for interval approximate that's of alternating infinite series. And I have here this explanation, right, of what we are calculating. I went ahead and brought out the theorem here in a bit of a condensed form. And it doesn't look too much different than the case for a non-alternating series. The big difference being what we add on, or in what we notice on the left-hand bound here, what we end up subtracting from the values of s sub n on either side of this interval approximation. On the lower end of our interval approximation for s, we take s sub n, this value that we're summing up through, right, the first n terms of our infinite series, and subtract this quantity given by the absolute value of a sub n plus 1, right, where a sub n plus 1, right, its absolute value, right, is the absolute value of the arguments of our series, well, I should say the arguments of our series up through the nth plus 1 term, or really I should say is the absolute value, the nth plus 1 argument of our series. Right? And we're going to subtract that absolute value and add that absolute value to both ends of s sub n, right, to produce our result. All right? So much of what we're going to do is very, very similar to what we saw above. So I'm going to go ahead and pretty much to begin with, go ahead and just copy this entire program down to this program. There's going to be a few small changes. One of those changes being that we are going to have an alternating series here. So maybe I make this a convergent alternating series. Let's go with the series -1 raised to the kth power times 1 over k plus 3 cubed. Now let's go ahead and simplify that again. Let's go down to just simply k cubed. All right. This is the alternating p series for the case where p is equal to the value of 3. Let's start at 1. Let's go back up to just 10. Keep it simple. Right. We are going to sum from 1 to 10 in this alternating series. That is going to be given by the value of s sub n here, right? Which can be numerically approximated this way. But what then also changes are these lower and upper bounds, right? Instead of using the lower and upper bounds given by the improper integrals, keep in mind we're just going to use the nth plus 1 term in our series, the absolute value of the nth plus 1 term in our series. So here I might take, let's see here, we're going to have to take the absolute value. Now to do absolute value in your calculation here in Mathematica, you are going to use the ABS function. That stands for absolute value of f evaluated at the nth plus 1 term, right? It's going to be the nth plus 1 term of our infinite series, and that is going to be given by the value of f at n plus 1, right? And then for the lower bound, it's going to be the opposite of that absolute value of f at n plus 1. All right? Now with that is all I have to change, I do believe. Because I incorporated the minus up into here, s sub n added to this lower bound will be a minus this absolute value, and S sub n added to this upper bound would give me the positive of that result. So I now believe if I want to go ahead and let's see what, well, we have the sum in decimal form. Let's leave it alone. If we hit enter, here becomes our interval approximation, right? And actually, let me go ahead and put semicolons at the ends of these bounds so we don't see those appear in our results. And here's our results. Here's the sum of the first n terms, negative 0.9011116. Here is that interval approximation. It's somewhere between negative 0.901868 and negative 0.900365 in value. All right? So, folks, these two codes here, this code here, and this code here can be used to calculate those interval approximations in this first case for non-alternating convergent series, and in the second case, right, the case for an alternating convergent series. All right? I hope that helps you a little bit in your understanding, and at the very least gives you a way of beginning to check some of your answers and to get through some of your calculations, folks. And again, being familiar with how to use my Mathematica is certainly going to be a skill that you're going to benefit from for the rest of your hopefully college career, math career, as well as perhaps your science career. So again, these demos are a good introduction to the Mathematica programming language. So folks, with that said, I will go ahead and stop this demo here. I know I have another demo that I want to put together for you that is looking at our fundamental tests for convergence, and I might incorporate into that the alternating series test, as well as maybe a ratio and a root test in all that. So I'll be back with another demo, I hope, in just a short amount of time. Hope you're hanging in there, and I'll see you during the next one.